Hello everyone, I am Dr. Navjeet Kaur, Assistant Professor in Physics, Mata Gujri College, Fatehgarh Sahib. Today, I am going to present the practical demonstration of the experiment based on PN junction diode. The aim of the experiment is to study the volt-ampere characteristics of PN junction diode for forward and reverse biasing. Let's start with the basic definition of P and N-type semiconductors. Semiconductors like germanium and silicon, when doped with trivalent impurities like boron, indium, gallium, are known as P-type semiconductors. In these semiconductors, holes are majority charge carriers and electrons are minority charge carriers, while when the semiconductors doped with pentavalent impurity like phosphorus, antimony, arsenic, they are known as the N-type semiconductors. In these semiconductors, electrons are majority charge carriers and holes are the minority charge carriers. But these P and N-type semiconductors acts like a resistor, and when they are taken separately, they are of no use. By doping one side of the silicon crystal with P-type impurity and other side of the same crystal by N-type impurity, a PN junction is formed. Thus, a junction is the boundary where P-type and N-type regions meet. At the junction, there are no discontinuities of the lattice. Here is the symbol of PN junction diode. PN junction diode is a two-terminal device where P side act as the anode and N side act as the cathode. Here we will discuss the types of biasing of PN junction diode and the formation of depletion layer. No biasing. It is the condition when no external battery is connected. In this situation, when P and N regions are joined, the majority charge carriers electrons from the N region starts diffusion towards the junction, enters into the P region and combine with the holes of the P region. Similarly, holes from the P side has the tendency to diffuse towards the N side and recombine with the electrons on the N side. So whenever electron leaves the N region, it leaves behind the vacancy of electron and it becomes the positively charged ion. Similarly, when holes diffuse from the P side, it leaves behind the negatively charged ion. Therefore, positive charge is built on the N side and negative charge is built on the P side of the junction. These ions are immobile ions. The difference of the potential from one side of the barrier to the other side is known as the potential barrier. This barrier restricts the diffusion of electrons and holes across the junction. The region containing these immobile positive and negative charge is known as the depletion region. Forward and reverse biasing. In the forward biasing, the positive terminal of the battery is connected to the P region and negative terminal is connected to the N region. These voltages of the battery repel the majority charge carriers towards the junction, due to which there is a reduction in the potential barrier. It means the width of the depletion layer decreases. Due to these repulsions, a large number of charge carriers can cross the junction and recombine on the other sides, which creates a large amount of current through the circuit. The current in the milliamperes flows in the forward biasing, while in reverse biasing, the negative terminal of the battery is connected to the P side and positive terminal is connected to the N side. The majority charge carriers are displayed away from the junction. Therefore, the depletion layer increases. Due to the increase in depletion layer, the majority charge carriers can't cross the junction. Therefore, the junction offers the high resistance and the flow of current is almost stopped. Only the minority charge carriers can cross the junction and they constitute very low reverse saturation current of the order of microamperes. Next is the voltage current characteristics of the PN junction diode. The graph between the voltage applied across the junction and current flowing through it is known as the volt-ampere characteristics of the PN junction diode. When we connect the circuit in forward bias, from the graph, the region OA shows that there is slight increase in current with increase in voltage because till that barrier voltage is not achieved. Once the barrier voltage is achieved along the curve AB, the slight increase in voltage produces the sharp increase in current. Then the curve along the region AB, it has a linear rise. While for reverse biasing, majority charge carriers are pushed away from the junction and it has a high resistance which prevents the flow of current. But as we increase the reverse voltage, the minority charge carriers, they are accelerated and they result the small current which is known as reverse current of the order of microamperes. So, the reverse voltage at which the current starts increasing, it is known as the breakdown voltage. It can be seen in the graph. Thanks. Now we will go to lab for the practical demonstration of the experiment.
Let's start the practical session. First, we will make connections for forward biasing. In forward biasing, the positive terminal of the battery will be connected to the P side of the diode and negative terminal of the battery will be connected to the N side of the diode. As we know, in forward biasing, width of depletion layer is thin. Therefore, large number of majority charge carriers can cross the junction and the flow of current is large, which is in the milliamperes value. So we will keep this switch at milliamperes value and the value of voltage is kept at the 1.5 volts. To study the VI characteristics, we will increase the voltage in small steps from this knob, from this forward bias knob. You can see with the slight increase in voltage, initially no current flows until the barrier voltage is achieved. Once a barrier voltage is achieved, which is 0.3 volt for germanium and 0.7 volt for silicon, the current rises sharply. We can see after the barrier voltage is achieved, there is a sharp increase in current value. The voltage at which the current increases sharply is known as the knee voltage of the diode. Afterward, with the increase in voltage, the rise in the current value is linear. We get the linear graph afterwards. Now we will make connections for the reverse biasing. In reverse biasing, the positive terminal of the battery will be connected to the N side of the diode and negative terminal of the battery will be connected to the P side of the diode. As in reverse biasing, the resistance of the diode is very high and current of microamperes flows through the circuit. Therefore, we will keep this switch at microamperes value and the value of voltage is kept at 90 volts. That is at reverse bias switch. Now, we will increase the voltage in small steps from this knob and we will note the corresponding current values from this ammeter. So, we can see in the reverse biasing, with the increase in voltage value, the flow of current is very small. That is, majority charge carriers can't cross the junction. Therefore, negligible current flows. But as we further increase the reverse voltage, beyond the certain voltage value, the current starts increasing. The value of voltage at which the current start increases, that is known as the reverse breakdown voltage. Afterward, there is a sharp increase in the current value. So, by note down the reading of current corresponding to the voltage values, we can plot the VI characteristics for forward and reverse biasing of the PN junction diode.
Thank you for watching the video. I hope this will be helpful to you for understanding the concept of PN junction diode and its working.